Hello. Hello.
Yeah, hi. Are you
Yeah,
there?
yeah. Hello. Yes, yes, yeah.
Just a minute. I have changed the network. Let us see.
Yeah.
Fine. Okay, let me see the curvature what it is. So first is uh, X-rays, nature of X-rays. Okay, right. Actually, it is a very big topic. It's not that easy.
Yeah.
We have to understand
Okay.
this X-rays. Basically, X-rays and gamma rays is not that much useful.
Mm-hmm.
X-rays are, because we know that whenever something happens to our bone, we normally take
Yeah.
X to understand the level of fracture in our body, right?
Yes, and also I think they can be used in planes, for example, to detect any cracks in the wings. They put the X-rays, and if there's any cracks, they can see. So, for example, when they're building for example, a submarine or something, they can identify any cracks by placing an X-ray through it.
Yes. So let us first discuss the most famous Rondon experiment. So
Yeah.
actually, Rondon was the scientist who has discovered X-rays. Means he has discovered some highly energetic rays, but its nature not known at that time, because at that time, like electron and all these things were not discovered. So Rondon he found that some energetic rays are coming out. So just because of its unknown nature, he termed it as X-rays, and till now we are using the X-rays in the honor of Röntgen, because we can rename it, but we are not doing it just to give the credit to the person who has discovered it, right?
Yeah. Yeah.
Actually, Röntgen, what he has done, I am telling you in brief. What happened? He was actually doing experiment. He was actually doing experiment on electric discharge. On electric discharge, he was trying to make one arc, electric arc, right? So
Okay.
he was doing the experiment on electric discharge tube, and basically the experimental conditions that was kept at that time was that pressure inside the tube was approx 10 to the power minus 3 millimeter mercury, right? So this is a very,
Yeah. Okay.
do you know what is the normal pressure in our air?
Um, it is one atmosphere.
Yes, 1 atmosphere, but in terms of millimeter of mercury,
Uh,
how much it is?
uh, I'm not sure the conversions. No, I'm not sure.
It is about 760 millimeter mercury. That means we say that
Okay.
76 centimeter mercury. This is the normal pressure. That is 1 atmosphere,
Okay.
right? So
Okay. Yeah.
he has kept the pressure as 10 to the minus 3 millimeter, which is very, very low, very low. So at the very, very low pressure, and he has applied a potential difference across the tube. He has basically made one tube that we will discuss just after this. So he made the he kept the potential difference between the anode and cathode as 25 kilovolt. So which is very high.
Okay. Yeah.
Is very high, right? So he found that when he maintained a pressure, when he maintained a very low pressure and a very high potential difference between the anode and cathode, he got that some unknown radiation were emitted, were emitted by the anode,
Okay.
not the
Okay.
cathode, by the anode. This is important. Anode
Okay.
means the plate which is connected to the positive side of the battery,
Yes. Yeah. 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 Yeah.
right? So this unknown radiation, he told that it is X-rays because it is highly energetic, right? It is highly
Yeah.
energetic. Now
Yes.
we know that
Yeah.
how this is produced. Yeah, tell me.
Yeah. I've got a question. So electric discharge tube, that means, is it discharging the charge?
No, electric discharge tube means it's basically this type of structure.
Okay.
A type of this is a glass tube, and
Yeah.
keep one plate here, another plate here. You connect this plate to one side of battery and this to another side of battery. So this will become anode, this will become cathode, and you are trying
Okay.
to maintain a potential difference between them, and you are trying to generate some discharge across it.
Oh, yes. Yeah. 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 Yes.
You're getting it?
Yes. Yeah. I mean, there must be something shining on the cathode to
Yes,
remove the
yes,
electron.
yes, yes, yes. So they have, so it was really very shocking that when he maintained a very, very low pressure and very high potential difference across the two terminals, this anode got, there were some radiation across anode.
Okay.
Okay,
Okay.
means
Yeah.
there was some radiation which affected the other particles also. So that means anode is producing some radiation whose nature was not known at that time.
Oh, okay.
But
Okay.
now we
Yes.
know, that this unknown radiation was produced by bombarding high energetic, means highly energetic electrons which was emerging from the cathode on a target which was placed on the anode, and this target should have high atomic weight and high melting point.
Okay.
Got
Okay.
it?
Yes. Yeah. Yeah.
So,
So,
in a single statement, yeah, tell me.
so I was gonna ask you, so what would the material be made up of?
Uh,
The anode.
we will see, So I can simply write X-rays are produced, because now we know the reason. We know that X-rays are produced by, let me write down the statement because this is important. This is a single line statement. So X-rays are produced by bombarding high speed electrons on a target of high atomic weight and high melting point. Now any material can be used. See, any material can be used which is of high atomic weight and high melting
Okay.
point. For example,
Yes. Okay.
gold, it may be gold, it may be tungsten.
Yeah.
Tungsten is having high melting point.
Yes. Yes. Yeah.
So we can use such material and many more material, maybe some alloy which
Yeah.
fills this criteria. But this was the original source for production of X-rays, right?
Okay. Yes. Yeah.
So this first slide means whether you have understood this one, that what was the Rondon experiment? Very simple one. He
Yes.
used one electric discharge tube and he was doing some experiment, right? Maybe he want to do some, he want to produce some arc or something like that. But he,
Yeah.
yeah, tell me.
I was going to ask you, so is this tube in vacuum?
Yes, good question. See, this should be fully, actually this should be vacuum. Actually, this should be vacuum, right? And if it is not vacuum, then you make the pressure very, very low.
Oh, okay. So
Okay?
so that there is no resistance.
Yes, there should not be any resistance from the air particles.
Okay.
Not
Okay.
resistance from the air particles. Yes, you got it.
Okay. Yeah.
So, see, in this page number 256, in the first it is said that William Rondon discovered X-rays in 1895. Okay. He was investigating the light emitted by gases in a discharge tube when a potential difference is applied between its two electrodes, right? So here, see, you can see this figure 1. It is this discharge tube is given. This is the discharge tube.
Yes. Yes. Yeah.
Right?
So it says gas at very low pressure. Yes.
Yes,
Okay.
it is gas at very low pressure. Effectively, we should vacuum it out. We should vacuum the gas, but it is not that possible that you are in nowadays with our latest technology, we can do it. We
Yeah.
we can make the entire tube vacuum, but at that time it was not possible. So
Yeah.
to make the pressure very, very low. So he seen that yes, it is given when the gas in the tube was at extremely low pressure, the tube went dark, but he noticed that a fluorescent plate near his apparatus glowed. When he placed his hand between the tube and the plate, he could see shadows of the bones in his hand. The unknown
Okay.
were passing through soft tissues, but were stopped by bone. So
Okay.
this was obviously very important discovery.
Yeah. Yes. Yeah.
Later on, we know that what is this. So any doubt on this one?
No.
Okay.
So my question is, there's a picture right next to it. So X-rays normally produced, as far as I know, in black and white. So how are X-rays producing colored images?
X-ray is not producing colored image. It is our that final editing software which is producing it.
Oh, okay. Yeah, okay.
So that is the thing. So any doubt about this? So this is important. This how X-rays are produced. This is important, and what we do is so okay. So obviously, based on this experiment, can you guess how could this Rondon have died at that time?
Probably because of cancer.
Correct. That is all those scientists, including Madame Curie, her husband, everyone who was
Yeah.
doing some research on any electromagnetic waves, dangerous electromagnetic waves. Almost all of them have died due to cancer.
Yes. Yeah.
But they died because of the good reason. But nowadays also people are dying out of cancer, right?
Yeah. Yes. Yes.
Doing smoking and all these things.
Yes. Yeah. That's right.
So, right. So now can you tell me what are the things required to produce X-rays?
Okay, so far we've seen that we need a electric discharge tube. Yes, so we need high voltage potential difference so that it can push the electrons from the cathode to the anode, so it's
Correct.
bombarding the anode side, and which, yes, and then it needs to be in very low pressure so that there is minimum resistance from the air particles. And
Correct.
yes, and also, yeah, I think those are the three conditions, main conditions.
Okay. So first thing, see, we have to bombard high speed electrons. So we need source of electrons, is it not?
Yes.
We need some source of electrons.
Yep.
We have to bombard this high speed electron on the target, which is having a high atomic weight and high melting point. So this is also required.
Yes. Yeah.
One target which is having high atomic weight and high melting point, is it not?
Yes.
Where we can strike this electron. And third, see, you have source of electron, you have target. But if your electron strikes the target at a low speed, it is of no use. So you
Yeah. Yeah. Yeah.
accelerate the electrons. So there should be some means of accelerating electrons. That's it. Acceleration of
Yes.
electrons so that it can strike it. Now, condition you have to put it. First condition is that pressure should be very, very low. Pressure should be very, very low, right?
Yes.
It should be very, very low. Then we can say that potential difference should be very high. So these are the two conditions, and these are the three resources that we require. If you have these five conditions and resources ready with you, you can generate X-rays, as simple as that.
Okay. Okay. Yeah.
Correct?
Okay. Yeah.
So to produce X-rays, nowadays we use X-ray tube. We use X-ray tube. Earlier we have used Cooley's tube. So Cooley he's a scientist who has developed one X-ray tube. Okay, so sometimes these X-ray tubes are also known as Cooley's tube. X-ray or Cooley's tube. So it is basically same as that of the electric discharge tube, but of advanced version where it has got source of electron, where it has got target, it has got some means of acceleration of electrons, right? So let us talk about the Cooley's method or Cooley's tube. Cooley's tube. So normally what will happen? We have to take, see, let us try to understand this. We have to take one filament. This is a filament.
Yeah.
Right? This is a filament, and okay. So this is a filament. So I'm just to make it in a good way. Let me. So this is a filament, and let us take one target. So this is the target.
Yeah.
It is the target, right?
Yes.
And in this target, normally in actual in hospitals and in medical research laboratory, what happens is there is a source, there is a tube where which contains water, So let's say water into it and water is coming out of it. A reason you will understand. So this is target. This is the target. This is the filament. This is the filament. And then what we will do is we will connect this to, we have to make it cathode, right? So we will connect to very high voltage, you can say terminal. So it is negative, and this I will connect to positive.
So is this a thermionic emission then?
Yes, correct.
Okay.
So this and now we are maintaining one potential difference of Vs here. Let's say it is V0, right?
Yeah.
This is the accelerating voltage. Let me write here. This is the accelerating voltage. So VA. Should. Now we have to enclose this entire thing in a tube, so which is normally made up of glass, so that we can see what is happening here.
Okay. Yeah.
I cannot. So something like this. Okay. So something like this, you can, like there are now enhanced structure, like normally it is like this,
Yeah.
something like this. Normally you will get X-ray machine like this one. So inside this you will have one
Yeah.
filament, one this target one, this target material, and there will be one source, one inlet of water and outlet of water, right? And you have to put this to very high potential battery resource, right?
Yeah.
Okay. And there will be, obviously there will be one window. There will be one window, and
Yeah.
here is the patient. Here is the patient, right?
Okay. Yeah. Okay.
Okay. Now, as you have predicted correctly, what happens is, first we will use this plus and minus to hit this filament. When this
Yeah.
filament will be heated, it will produce electrons,
Yes.
right? But since this cathode and this anode is connected to a very high voltage terminal, so these electrons will be accelerated. These electrons will be accelerated while it is moving from cathode to anode. That means it is gaining a very high energy, and with a very high will strike the target. And
Yeah.
when it will strike, we can see that there will be some radiation which will be coming out from this particular window, and it will serve our purpose. Now you can make some mechanism so that it will fall on a particular let's say plate or some paper which can be further processed to see the structure of the bone fracture and so on, right?
Okay. I've got a question. So could this be going here as well?
No, because you are obstructing it. See, you have to make one window. You cannot allow the X-rays to go everywhere. So there are
Okay.
see, because you know that X-ray is being produced. So why we will allow the other parts to escape this particular X-rays, which is dangerous. We will
Yes. Yeah. Yeah. Yeah.
normally in a particular X-ray machine, that just for a fraction of second they will or maybe for 1 second they will keep this machine on, just for 1 second.
Okay.
Okay.
Yes.
Just for
Okay.
1
Yeah.
second they will keep the machine on, and it will work,
Yeah.
right?
Okay.
Okay, so see what is happening is, let us see the method once again. So electrons are produced by thermionic emission, right?
Yes. Yeah.
Due to the high potential difference between the cathode and the anode, these electrons will move towards the anode at a very high speed, and it will strike the atom of the target, due to which X-ray will be produced. Simple.
Yeah.
Now,
Yeah. Okay.
the internal mechanism in detail, but this is the brief of the entire story.
Okay. Okay. Yeah. Yeah. Yeah.
Now, interestingly, hardly 1% to 2% of kinetic energy of the electron beam, means these electron beams has got some kinetic energy due to this high potential difference, but
Yeah.
only 1% to 2%. Most efficient X-ray machine will give you 2%. So 1% to 2% of kinetic energy of electron beam is used to produce X-rays. Rest are wasted in the form of hitting the target atom. Hitting
Oh.
target atom.
Okay.
And this becomes so hot that if you don't make any mechanism to cool it, then it will be of no use. So that's why one water will be supplied to it so that it can take out the heat continuously. Are you getting?
Yes. Yeah. I've got a question. So what is being so we are bombarding the electrons with the target metal, right? And that produces X-rays, right?
Yes.
So what really produces X-rays? So what is
Okay,
the
we will see.
matter?
There are two methods which produces X-rays. Right now, just see that what is happening. But now this striking of electrons and production of X-rays, that we have to see. Now we are seeing
Okay.
how we can produce it in lab. So that was our,
Okay.
later on we will see that what are the methods, because there are two type of X-rays. One is continuous X-rays, another is characteristic X-rays, and that
Okay.
depends on various other factors also, right?
Yeah. Yeah.
We have not seen this one, just we want to look into the brief of how it is produced.
Okay. Yeah.
Okay, now can you tell me this target that we are using, what should be the characteristics of that target? Any idea? We have already
Yes. Yes. So it should be high. Should have a high melting point, and it should also have heavy atoms.
Yes. Why it should have high melting point? Now you can answer it.
So that it doesn't change phase while it's because, as you said, it gets really hot, and if it changes to a liquid, if it has a low melting point, it will turn to liquid, and it will be damaged.
Yes,
The
correct.
whole X-ray machine will be damaged.
So halting, so it must have high melting point to withstand very high temperature which is produced,
Yes, yeah.
right?
Yeah.
And then it should have a high atomic number. Means now why high atomic number? Because this atomic number, high atomic number, will produce more the atomic number, more hard X-rays. Actually, we will see there are two types of X-rays. One is hard X-rays and another is soft X-rays. Hard X-rays are dangerous, but it is more useful. Soft X-rays are less dangerous, but it is not that much useful. So if the atomic number is high, then this hard X-rays will be produced. Otherwise, soft X-rays will be produced, right? We will see that what are the different properties or differences between a hard and soft. We will see that one later.
Okay, yeah.
Third, can you tell me any other characteristics?
It should also have 1 second, high melting point, target. 1 second.
It should
Yes,
have high
it should
thermal
be.
conductivity.
Yes, yeah.
Why? Because it should remove the heat as soon as possible. Simple. It should have a high
Yes.
thermal conductivity to remove the heat that is produced. Right?
Yes. My question is, so are X-rays produced because of the heat, or okay? I think we're going to look.
No. We will see that one.
Yeah.
How these X-rays are produced, we will see that one.
Okay. Okay.
Now there are certain materials which serves all these properties, and the best is like one is platinum. We have tungsten. Yes, tungsten is also used. Tungsten means we are talking about target materials. So platinum serves platinum or tungsten, or we can use, there is, I think you have heard of molybdenum.
Yes, molybdenum. Yes, yeah.
Right. Then we have tantalum.
Yes. Okay.
So these are the normally used target materials.
Okay. Yeah.
Correct?
Yeah.
Now, okay. Now let us look into what are the why this X-rays will be produced. See, X-ray means it is just one electromagnetic wave, right? It is just electromagnetic.
Yes.
So why it is produced? Let us look into that. Okay, just so this production of X-rays, basically X-rays production, it is having production mechanism. There are two mechanisms in which X-ray may be produced. One is called continuous X-rays, and another is called characteristic X-rays. So actually what I have here, mm, what we have seen here. Okay, characteristic of target. Can you tell any idea that intensity of X-rays, how we can increase the intensity of X-rays and how we can increase the energy of X-rays? Any idea? Then we will go there.
Yes, so first we can increase the energy by increasing the speed of the electrons, because as we know that energy is conserved. So by increasing the kinetic energy of the electrons, maybe we can increase the energy of the X-rays.
Right.
And intensity is related to more number of X-rays. So the more number of electrons are colliding with the anode, the higher the intensity. Is that correct?
See, intensity means what? Intensity means, see, assume that X-ray is a photon, right?
Yes.
So more intensity means more number of photons. How you will?
Yes.
Do you remember photoelectric effect? That photoelectric current. How you will increase photoelectric current?
By increasing the number of electrons.
And yes,
So
the number of electrons.
Yes. So for that to happen, we need more photons.
Correct.
Because
Correct.
So here we need to increase the number of electrons.
Correct. Very good. So that means we have to heat it more.
Yes.
That means we have to use high potential difference across the filament to get more intensity.
Yes, and we can increase the kinetic energy increase the energy of the X-rays by just increasing the kinetic energy of the electrons.
Correct. So many a times this is asked that how we can increase the energy level of X-rays and how we can increase the intensity of X-rays. So both are different. Intensity of X-rays means density of X-rays. Density of X-rays will increase only when you increase the number of electrons, and these electrons, number of electrons will depend on how much you are hitting the filament. Whereas energy of X-rays will depend upon the accelerating voltage, as you have told that it depends on the kinetic energy of the electrons, right?
Yes. Yeah.
Okay. Now, when these X-rays are analyzed over a particular graph, graph look like this. So intensity of the X-rays versus wavelength of the X-rays. It has been found like this, something like this.
Okay.
Like this, it has been found. This is very interesting. This type of graph is seen on analyzing the X-rays. Now here, see, that this graph contains of two things. One is a smooth curve, another is a sudden spike in the graph, right?
Yes.
Okay. This continuous graph represents continuous spectrum of X-rays, whereas this spike, it represents characteristic spectrum of the X-rays. So continuous means this continuous curve that we are looking into.
Okay.
Characteristic means it is the spike, it is the sudden increase in the intensity of the X-rays, right?
Yes. Yeah.
Why this is produced, let us see. What is actually happening is, let us talk about the continuous spectrum. So see, when this is the target, and this is the electron which is coming towards it. So let me write it. This is the electron which is coming towards it, right?
Yep.
When this electron is coming to strike the target, what is happening is there is some there is some repulsion to this electron due to already present electron in target material. Is it not?
Yes, yeah. Because yeah.
And due to this electron is getting decelerated. This
Yes.
electron is getting decelerated. See, as simple as that. If this is the single electron which is moving towards it, and if you have a cloud of electrons, then obviously when it is trying to reach near it, its acceleration will be its speed will be reduced. That means
Yes.
it is having negative acceleration, right?
Yes. Yeah.
Okay. And we know that whenever any charged particle accelerates or decelerates, it will produce electromagnetic waves. Is it not?
Oh, yes. Yeah.
See,
Okay.
during the deceleration of the electrons, what is happening is energy is decreased, obviously, because at one moment it will be having zero energy.
Yeah.
Its energy is decreasing. This loss of energy during the deceleration is emitted in the form of X-rays.
Oh,
This
okay.
is one mechanism.
So what happens if there is zero energy of the electrons when there's zero kinetic energy? Because so we
See, I'll tell you, this is happening when it just enters the target. It will never happen before it. It has entered the target. Now what will happen? Tell me.
I've got a question. So how can it enter it? Wouldn't it be repelled after? Because it will be closest distance. Sorry, it will be repelled. So we've seen work. So there is work energy principle here. So there will, so at a distance the energy will be zero and it will never
Now every question will be answered. We have already seen that we are taking a target element of having high atomic weight. High atomic weight, that means for a single atom you will have large number of Bohr orbit. Is it not?
Yes. Yeah.
Okay. So let's say this is the target atom, just one atom. I am showing just one atom. So let's say this is one electron, this is one electron, this is one electron, which is moving in this. So this is the electron. These are the electrons which are revolving in the orbit. So I'm just for example, I have shown all these things, right?
Yeah.
When the actual electron, when the outside electron, which is being accelerated by the anode potential, when it enters here, whenever it enters here, see, there are two things. This outside electron, it may strike any electron or it not strike any electron, right? Only two possible.
Yes.
Assume that it is not striking any inner electron of any atom. Then see, let's say if it is entering it with a speed of v1, then obviously what will happen is it will try to enter here, but due to repulsion it will be diverted to some other angle. So it will emerge out with a speed of v2. This is one possibility. Possibility, right? Now obviously v1 to v2 energy will be reduced.
Yes.
This energy reduction will take place in the form of heat, in the form of wave. So it will come out. It will come out as simple as that. It will come out. So X-ray photons will photon will come out.
Yes. Okay.
Are you getting it?
Yes. So I think when it goes past this, it produces a photon of specific wavelength. Could that be determined by the material it is, going into? Because that would determine the speed.
No,
Because that
no,
would
no, 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 no. Good. It will not be, see, okay. Let us see one by one. So what is happening is when high-speed electrons collides from the atom. See, collision does not mean that it has to strike it physically.
yeah.
When the high-speed electron collides from the atom of the target and passes close to the nucleus, then obviously this electron will be decelerated. And this energy, this loss of energy during deceleration is emitted in the form of X-ray photons. Such type of X-rays are called breaking or one another name is there, Bremsstrahlung. It is called Bremsstrahlung radiation. I think yes. Bremsstrahlung radiation. This is called breaking or Bremsstrahlung radiation.
Yeah.
Right? And this radiation forms continuous radiation. It forms continuous spectrum. In continuous spectrum, all the wavelength of X-rays are present. All the wavelength of X-rays are produced, but below a minimum value of wavelength, there is no X-ray. But below a minimum level of wavelength, there will be no X-rays. It is called threshold or minimum wavelength of X-rays. This minimum wavelength depends on the applied potential. How this is possible? I am trying to just okay. Let me go into detail that why all these are possible. See, what is happening is, what is the loss in kinetic energy? So if I write loss in kinetic energy of the electron, right? It will be initial energy was half mv1 square, right? Half mv2 square. Now this loss and energy will be produced by this electromagnetic wave and the heat energy. Right? Now, if assume that if let's say this electron losses full its energy, means if the energy loss is maximum, then I will write V2 is equal to 0, and let's say equal to B. Correct? And assume that there is no heat energy, all entire loss in kinetic energy is converted into the X-rays. So I will say that heat energy is equal to 0. Okay? So in this case, if we apply this data, we will get the above equation becomes half mv square is equal to h nu max, is it not? That means it is equal to SC by lambda minimum. And this half mv square, how it is coming? It is coming due to EV, where V is potential is applied across the two plates. So these are the defining equations for continuous spectrum. Let's say you have to find out what is the minimum wavelength of the continuous X-rays. So you have to say it depends on the applied potential difference. Are you getting it?
I understand.
So I can write like this: lambda minimum is equal to EV by SC. Is it not?
Yes.
So you know the value of E, what it is?
1.6 times 10 to the power minus 19.
Just a minute. I think I have made some mistake. It will be SC by EV. Because
because energy is
SC by okay. So just opposite. So I know the value of H.
So
it will be how much?
6.63 times 10 to the power minus 34.
And what's the value of C?
3 times 10 to the power 8.
by 1.6 into 10 to the power minus 19, right?
Yes, yeah.
Into 1 by V. So if you calculate it, how much it is, you will get a
Yeah.
important formula. It will be lambda minimum is equal to 12400 by V Armstrong,
Okay, yeah.
right? So
Yeah.
you should remember that this threshold wavelength of continuous X-ray. Always remember, threshold wavelength exists only for continuous spectrum. We have not started yet this this statistic spectrum. We have just seen what is the continuous spectrum, right? So
Yeah.
spectrum, this continuous X-rays are also known as white X-rays. These are also called, sometimes in many of the books I have seen, these are called white X-rays. So
Okay, yeah.
wavelength of these X-rays depends only on the applied potential, and it doesn't depend upon the atomic number. It doesn't depend upon the target material. It depends only on the anode potential.
Yeah, okay, yeah.
Okay. Now,
Yeah.
this is continuous. See, because it may produce, because it at every instant this V2 may be different. V2 may be different. That means at every instant this frequency will be different. Is it
Yes.
okay?
Yes, yeah.
So okay. So tell me, if V is more, lambda minimum, this threshold wavelength, whether it will decrease or increase.
So is this V initial or final?
Oh, this is anode potential. This is the potential difference.
Oh, potential difference. Okay. So that means it would
See,
decrease.
this V is potential difference. Don't get confused with velocity.
Yeah. EV is the energy. Yes, yeah. Of the electron. Yes, yeah.
So I'm asking you that if I increase the potential difference between the two plates, two electrodes, what will happen to the threshold wavelength?
It should decrease.
It should decrease. Very good. It means that if I draw a graph like this, so intensity versus lambda. So we have used two potential difference, and graphs are like this. So this is the graph when I used V1, and this is the graph when I used V2, potential difference V2.
Okay.
So this is lambda 1. Can you tell me which one is more? V1, V2? Which one is more?
Yes, V2 is slowed down, so that means lambda 2 is greater than lambda 1.
No. See, lambda to lambda 1 are abstract. You can make out the abstract comparison. That is lambda 2 less than lambda 1, right?
Yes, yeah.
It means that V2 is greater than V1. The more potential difference, more it will come here. More it will come here.
Okay.
Are you getting it?
Yes, yeah, because lambda value would be smaller and then it would increase the value of V.
Yes.
No. Yes, yeah, because the energy would increase. That means the velocity will also increase. Yeah.
Correct, right?
Yeah.
Okay, let me see the carbidal. So here, see, we have already seen nature of X-rays. These are harmful to, these are not required. Production of X-rays. Already we have discussed, I think. We have taken.
Yes, we've seen this, yes.
Okay. Target metal is there. Okay, picture figure 5. X-ray tube is given. Fine.
Yeah.
So we have already seen.
Yeah.
Then we have the shortest wavelength. So shortest.
Yeah.
This
We've seen this now.
yes, we have just seen.
Yeah.
So maximum content. Okay, fine. Now what they have given? Yes, after that they have given characteristic X-ray. That we will see. That
Okay.
we will see.
Okay.
So 60. electrons.
So I've got a question. So they've given a graph intensity of X-rays against wavelength, just as you did. But they've named it differently. Are there different
One is,
names?
yes, they have named as bremsstrahlung. We have already discussed. Bremsstrahlung means what? See, I think I have not, I have told you this now. This, see, this bremsstrahlung. This continuous, see, this continuous spectrum, this continuous radiation is also known as braking radiation or bremsstrahlung radiation.
Okay, yeah, yeah, because this is continuous. Yes, yeah.
Yes, this is continuous, right?
Yeah, yeah.
And that sudden spike, it is because of characteristic X-rays.
Yes. Okay. Okay.
Okay. Now, let us see the other type of spectrum, that is characteristic spectrum.
Yeah.
Characteristic spectrum. Okay. So there is a name associated with this characteristic spectrum, means there is this name of the scientist, Moseley, right? And he was killed, I think he was killed in World War II at the very young age of, I think, 30 years.
Oh, okay. Okay.
Okay, but means had he been if he hadn't died in that World War, he would have discovered many new modern physics theories.
Okay.
Right, because at the very young age he died because he was very interested in fighting the war.
Yeah. Okay. Okay.
So anyway, we will see that what is the theory or what is the formula that he has given us.
Yeah.
Characteristic spectrum. See, obviously, we know that this, let's say this is the target atom, right? This is target atom. And let's say there is one electron here, there is one electron here, there is one electron here. So there are so many electrons. And with that, it is K, L, M, and so on. We can name the orbits as K cell, L cell, M cell, and is it not?
Yes. Yes.
Now, one high-speed electron, it has already entered the territory of this atom, and we know while it enters, it will continuously you're producing the continuous spectrum, right?
Yes. Yeah.
Okay. Now, there is a possibility that this electron will strike some other electron which is already orbiting inside the target atom. And this electron, since this electron is with some energy, this electron will knock out this electron and it will go out, right? It will go other place and it will vacate it. It will vacate it. See, actually what is happening is when this highly accelerated electron, right, strikes with the atom with the target atom, then there is a possibility that it will knock out the electron of the orbit, right?
Yes. So this will gain some energy. That means if it has a specific energy, it will go to a specific shell. For example, it could go to L, it could go to M, and go to N. But then it will come back again, which will then emit X-rays in terms of photons.
No. Let me clarify it. What is actually happening is when this outside electron is hitting the inside electron, then both these electron will lose energy and they will collide somewhere else and they will hit it, right? They will hit the atom. This will hit the target. But what is actually happening is this knocking out of electron creates a vacancy. It creates a vacancy, and to fulfill this vacancy, some other electron from the same atom will come, and due to this, it will radiate energy. We know that whenever any electrons jumps from higher orbital to lower orbital, it will emit some energy. Is it not?
Yes. Yeah.
So this energy, this radiation is called characteristic X-rays.
Yes, yeah.
To,
So
to fill this vacancy, electron jumps from higher energy level and electromagnetic radiation are emitted, which form this characteristic spectrum of X-rays.
oh yes, yeah, I understand. Yes, yeah. So yes, so this electron, the external electron is removing the electron inside the atom. Is
Yes,
completely it, and the new electron from the outer shell is
yes,
coming down, and that is emitting X-rays. Okay.
correct. And such type of X-rays will depend only on the target atom. That's it. It depends on the target atom. It does not depend upon characteristic spectrum X-rays, does not depend upon potential difference. It
Yes, oh yes, it's
target
obvious
atom.
because the distance between the two shells represents the energy, and obviously it's different for different atoms. So yeah,
Right now,
yeah.
there is one more interesting thing here is, say, if let's say for characteristic X-rays, we normally denote it using some notation, right? So it's like this, that if the original electron, see, if the original inside electron, if it was initially in the first orbit and the outside electron strikes it, it removes it. So vacancy is created in the innermost cell.
Yeah.
To fulfill this vacancy, now outer cell electrons will come. That means electrons from 2, 3, 4, or so on, they will come, right?
Yes.
This series is called K series.
Oh, okay. Yeah.
Called K series because N1 is equal to 1 means it is the K cell, right?
Yes. Yeah.
Now, interestingly, if from the first, let's say vacancy is created in the K cell and electrons from the second cell, if it comes to fulfill it, then I will name this X-rays as K alpha X-rays. It is called K alpha X-rays.
Okay. Yeah.
If
Yeah.
from the third cell, if the electron moves to N1 is equal to 1, then I will say it is K beta. Similarly, it will be K gamma, and you need not worry about others because everything will be like you will not be asked beyond that. So K alpha X-rays means what? See, K alpha X-rays means initial vacancy was created in the K cell and electrons from the just one cell ahead, that means from the L cell, electrons is getting is jumping to this vacancy, and due to this, that X-ray, when X-ray is produced whose wavelength is lambda, so this is produced by this one. Are you getting
I've
it?
got a question. Yes, I've got a question. Does the electron always does the external electron always knock out the electron in the K cell?
No.
Okay.
Possibility. This is percentage. Possibility. And it is a rare percentage, right? It is a rare.
Yeah.
And these characteristic X-rays are seen in the graph as spikes. So you can see spikes are very few.
Yeah. Oh, so okay, I understand. Yes, so that's why the intensity is really high.
Yes, intensity is really very high because just one electron is getting, so obviously intensity will be very high.
Yeah.
Are you getting it?
Yes. Yes, yeah.
So here, let's say, can you tell me what will be the naming of X-rays if vacancy is created at N2 is equal to 2 and the electrons is coming from See, okay, so let me rewrite it again. So vacancy is created in second cell, and electron is coming from fourth cell. So what type of X-ray this is?
So which is L gamma.
No. See,
Um,
L alpha means what?
the third.
L alpha means, see,
Oh,
already.
sorry. It's L beta.
Yes, it is L beta, because no electron will come from inside the cell, right? Inside the orbital. Inside orbital, nobody will come.
No. Yeah.
So L alpha means M to L. L beta means so K L M N. It means N to L. So are you getting it?
Yeah.
Right? Now, how we will understand how we will find out the wavelength of this characteristic X-rays. So it's very simple. What we have to do is just we have to see that from where to where this electron is jumping. So if electron is jumping from first orbit to second orbit, or let's say second orbit to first orbit, and due to this one X-ray is produced whose wavelength we have to find out. So I will write, it's very simple. I will write Sc by lambda is equal to energy of 2 minus energy of 1. That's
Yes. Yeah.
right. So
Yeah.
that means if we have to find out lambda k alpha, that means I will write Sc by energy of K cell minus energy of L cell. Is it not?
Yes. Yeah.
Right. So in this way, we can calculate the wavelength of the characteristic X-rays. We have
Okay. Yeah.
to the this thing, what do you call it? Mosley's law. There is one important law called Mosley's.
Okay.
Mosley's. So we have to see this. Now tell me one thing, that this spike, how you will understand that what will be this spike, right? K alpha, K alpha or K beta. Can you tell me if I draw like this? This is intensity versus lambda, and I have drawn something like this. So something like this. So we know that this continuous curve represents the Bremsstrahlung radiation, and this
Yes.
spike represents the characteristic X-rays, right?
Yeah.
So can you tell me that if this is K alpha, what will be this?
1 second.
This is very okay. Tell me whether this will be K beta or this will be L alpha.
1 second. Let me just draw. It is 1 second. Yeah. So this is K alpha, right? So this has a wavelength. So this has to be some other. I think it's L alpha because it has to be a different. Yes. Yes.
Okay.
Each spike.
Tell
I
me this
think.
thing. Okay,
Yeah.
no issue. Just tell me this thing. Wavelength of K alpha will be how much? Sc by what I will write? E
Yes. E K minus E L.
minus EL, right? Okay.
Yeah.
So lambda of L alpha, what I will write? Sc by
M. Sorry. EL minus AEM.
M. Can you tell me which difference is more? This one is more or this one is more?
Obviously the first one is more.
Why?
Well, no, sorry. It's the second one because Actually, it depends on the atom.
Now, see, I'll tell you why. Okay. See, for example, for a hydrogen atom, what will be energy of the K cell?
It is
Minus 13.6.
3.6. Yeah.
Right? Okay.
Yeah. 13.6.
Energy of the L cell. Minus 13.6 by 4, because 2 square I have to do.
Yeah.
So how much it is?
Yes. So it is 13.6, right? Divided by, I think it was 3.4 minus 3.4.
3.4 electron volt. What is EM?
1.5.
1.5, right? Okay.
Yeah.
So other than hydrogen atom, whatever atom it is, only you have to multiply by by Z square, is it not?
Yes. Yeah.
We have already seen all these things.
Yeah.
We have to multiply by Z square. So right now I am not multiplying it. Now tell me, magnitude of EK minus EL will be how much?
EK minus. Oh yes. Okay.
It
Yes.
will be how much?
So it is minus. Minus 13.6. The magnitude, right? Okay.
Yeah, 13.6 minus
13.
how much it is?
So it is 10.2. The magnitude is
10.2 electron volt. Okay. So what will be EL minus EM?
It's 1.9.
It is 1.9. Okay. So whose difference is more, this or this?
The first one, EK minus
First one,
EL.
right? So if you
Yeah.
multiply by Z square also, this one will have, it is more than this one, is it not?
Yes. Yeah.
Okay. So now tell me, which one is more, EK minus EL or EL minus EM?
EK minus EL. Yeah.
It is
Oh no,
more.
sorry. It's more in. So that means the lambda value would be less. So this would.
So
Yeah.
lambda K alpha will be less than lambda L alpha, is it not?
Yes. Yeah.
Right? So it is possible. It is not possible because if I write L alpha, that means this lambda L alpha will be less than lambda K alpha, but it is not the case.
Yeah.
Right? So it is not the answer. Let us check K beta. Right? So K beta means what we have to do? K beta means K beta. K beta means KLM. That means electron is jumping from M to K.
Yes. M to K. Yeah.
So what will be EK minus EM then?
Yes.
Only magnitude.
Yes. The magnitude is 12.1.
12.1, right? So it is more than EK minus EL.
Yes. Yeah.
That means lambda K alpha will be greater than lambda K beta, is it not?
Yes. Yeah.
So it means that this will be K beta, this will be K alpha.
Yes. Yeah.
So you are 100% sure that it will be. So it does not depend upon, see, this to just compare this, to compare the value. See, always remember, to compare the value of this K alpha, K beta, you need not require the atomic number. But if you want to calculate the lambda, exact value lambda, you require what type of target atom it is.
Yes. Yeah.
Are you getting
Yes.
the point?
Yeah.
To just compare it, you can easily, you can just do it by the help of hydrogen analysis. But to calculate the values of lambda, you require what type of atom it is.
Yeah.
So any doubt here?
No, there is no doubt. No.
Now tell me, if I draw, let's say if I observe some another peak like this, and out of this one is L alpha and another is L beta. Can you tell me, let's say this is A and B. So which one will be L alpha and which one will be L beta?
Okay, yes, okay. So would L alpha be from the second minus the first, right? Yes, the second minus the first. Okay, 1 second. The second is 3.5. Sorry, second minus the third, sorry.
Yes.
So 3.4 minus 1.5, 1.9. Yes, L alpha is more. So
Yes.
that means that if L alpha is more, that means the lambda must be less. So it has to be A is L alpha and L beta is B.
No, wrong.
1 second. Okay. 1 second. So sorry. L alpha is less. Sorry. If it's less, then lambda has to be greater.
That
If
means,
L alpha.
see,
Yeah.
you have to first calculate energy of L alpha and energy of L beta, is it not?
Yes. So the energy of 1 second. The energy of L alpha is greater than. Sorry. Yes, is greater than the energy of L beta.
No, it will not be there. See,
1 second. Can you go back to the hydrogen?
okay, this was,
Yes. Okay. Yes. Okay. Yes. Okay. Oh, it's 3 point. Yeah. Okay. Yes. The 1 second. Is it alpha?
see,
Yes. So isn't it E? So L alpha is EL minus EM.
EL alpha is, yes, EL minus EM, correct?
Yes. So that's 1.9.
Then calculate EN.
Yes. So that yes, so it would get smaller and smaller.
Yes,
I
it
mean,
will be more,
magnitude
it
wise.
will be minus 0.51, right?
Yes. So the difference is less. So what I'm saying is the L alpha is because it has a greater energy, the wavelength would be smaller.
L alpha, so you are telling that L alpha will be have smaller
Will
wavelength.
have yes, because it has a higher magnitude of energy.
Is it? So EL minus EM is 1.9 and then you have EL minus EN. How much it is?
0.99.
See, why you are getting confused, I don't know. See, let me tell you one thing. Okay. See, if I write E cell, EK, EL, EM, EN, and so on, right? So
Yeah.
this is decreasing. This is in decreasing range, right?
Yes.
So obviously, if you take EK and EL, right? And if you
Yeah.
compare it with EK and EM. So if you are increasing the gap, you are getting more energy or not?
Yes. Yeah.
EK and EL will be, let's say this is okay, let's say this is 10 volt, this is 9 volt, this is 8 volt, this is 7 volt, right?
Yeah.
Okay. Now if you are taking the difference of EK and EL, obviously it will be less than EK and EM.
Yes. Yeah.
Because you are making the gap, right? You are increasing the gap.
Yeah.
See, EK minus EL will always be less than EK minus EM, and it will always be less than EK minus EM. Why? Because you are increasing the gap.
Yes. Yeah. Yes.
So
Yeah.
it means that K alpha will always be less than K beta, will always be less than K gamma. So this is in terms of energy. That
Yes, yeah,
in
yeah,
terms of
yeah,
wavelength, it will be L K alpha will be greater than lambda K beta will be greater than your lambda K gamma.
yeah. I think I realized my mistake. Yes. So L
And this
beta
same
means
thing,
yeah,
this same thing.
yeah.
So let me give you one trick. See, this same thing happens with L also. L alpha will be greater than L beta greater than L gamma. Are you getting it?
Yes, yeah. Yes. Can you go back to the other slide? The one we just doing. Yes, yes. So
I think you
the
have
question was
made some mistake.
yes. The question was L alpha and L beta, right? Yes.
Yes.
So that would be from L to M. N. Sorry, L to N.
L to N. Yes, L to N. So you are increasing the gap. Earlier,
Yes, yeah,
you were getting 1.9. Now you are getting
so it is 3.4 minus 0.51, right? So it's 2.89. So
definitely energy increases.
yeah. Yes, that means the wavelength decreases. So LB is A and LA is B. Okay.
Correct. So it will be L beta and it will be L alpha.
Yes. Okay. Yeah.
Okay. So
Yeah.
so in this way we can understand this. There are actually there is one more topic related to this, that is
Yeah.
Moore's law, that we will see. Let me check first what is this thing they have given in this book. So characteristic X-rays, okay. Characteristic X-rays, okay, lines. See in the figure 7 in page number 258, they
Yeah.
have shown how K lines are produced.
Yes. Yeah.
Okay, we
Yes.
have
Yeah.
already seen this one. That
Yes. Yeah.
gap, and due to this, it is making it. And then see question number 6. Can you do it? Summary questions.
Yes. Calculate the shortest wavelength of X-rays from an X-ray tube operating at 100 kilovolts. Explain your answer. Okay. Shortest wavelength of yes. Okay.
So first of all,
Yes.
you have to tell that this X-rays, this shortest wavelength of X-rays corresponds to the Bremsstrahlung radiation. Means continuous spectrum. Continuous.
Yes. Yeah. Yes. The shortest. Yes. Yeah. Yes. And the shortest wavelength, the magnitude is basically HC divided by EV.
Yeah, always use this 12 12400 by V. It will give you in a very short way.
Yeah. Okay.
Right?
Okay. Yeah. So yes. So the answer is 1 second. Yes, it is. Yes. Okay.
This one 12400 by V. So instead of V,
Yes.
write down 10 kilovolt.
Yes. So I got an answer of 1.24 times 10 to the power minus 11.
That is 0.1
So
strong.
yes. Yeah.
So that will be
Yeah.
the answer.
Yes. Yes. 0.1 Armstrong. Yes. Yeah. That's the answer. Yeah.
Right?
Yeah. Okay.
So
Yeah.
and okay. So now in the next chapter, they have given. Say try to solve all the summary questions, whatever it is given, and try
Yes, I'll do that.
this chapter. Now you will understand it.
Yeah. Yes. Yeah.
Okay. Now we have absorption. Okay. So absorption we will see it later on, right?
Okay. Yeah.
Okay. So fine then. Thank you very much. I will send you this slide in Skype. I don't know in Skype I have sent you on that day, but you didn't get it.
Yes. So is the email matching the Skype?
Yes, it's matching, but you have not received. Can you send me message? Just
Yes.
file number 704714222.
Okay.
in a
Yes. Okay. Yes. So can you repeat your number again, please?
just time. So it's 70. I'm writing it here. 7047142022.
1 second.
Here.
1 second. 1 second. I lost your screen. Yes. 7047142022. So is that your WhatsApp number?
Yes, this is my WhatsApp number.
Okay. 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 Yes. Okay. Okay. That's fine. Yes. Let me. Okay. So. Okay. 1 second. Yeah. Okay. Okay. Yeah. Okay. So for today's lesson, can you just send it to me
Your
on
WhatsApp.
WhatsApp?
Yeah,
Yes.
yeah.
Okay.
I'll send you.
Okay. Okay. Yeah.
Okay,
Okay.
then thank you very much.
Take care. Bye.
Yeah. Bye.